Good morning, everyone. So, we are looking into the integral transformation for the solution of partial differential equation. In the last class, we completed the Laplace transform, and we remember that we can use the transform calculus only in case of linear partial for the solution of linear partial differential equation. Now, in today's class, we will be looking into the Fourier transformation. In the case of Laplace transformation, it is basically used for the parabolic partial differential equations, which are typical for transient chemical engineering problem. Now, in case of Fourier transform, the domain is generally minus infinity to plus infinity, not necessarily you can take the sine Fourier transformation or cosine Fourier transformation and can bring down the problem into more amenable form. The basic idea of using the mathematical transformations are that they reduce the order of rigority of the problem. They reduce the partial differential equation into an ordinary differential equation, and if the governing equation is ordinary differential equation, they reduce it into algebraic equation. So, solution of ordinary differential equation is easier to solve compared to partial differential equation, and solution of algebraic equations are easier to solve compared to the ordinary differential equations. So, that is how one should use the transform calculus to reduce the rigority of the solution of the problem. Now, in today's class, what we will do, we have looked into detail of the Laplace transformation, their properties and the various methods to be used to solve the various problem using Laplace transform. And in today, we will be looking into the Fourier transform. First, we will be looking into the in the last class, we have seen some of the properties of the Fourier transform and definitions of Fourier transform, and then we will be in this class we will be looking into some of the properties of the Fourier transform and how they will be utilized to solve the partial differential equation. Okay. So, in the last class, what we did, we looked into some of the functions and had the Fourier transform of it. So, next we will be looking into another transform, the transform of another function, Fourier transform of, let us say, f of x, and f of x is given as minus e to the power minus a mod of x, where x lying in between minus infinity to plus infinity. So, mod of x, if you look into the definition, is that minus x for x less than 0, and this is plus x for x greater than 0. So, f of alpha, the transform domain, alpha is in the transform domain. If you write down definition of Fourier transform, it will be 1 over 2 pi minus infinity to plus infinity f of x e to the power I alpha x dx. So, therefore, we will break down this, since the definition of f x and the f x is e to the power minus a mod of x. So, definition of f x is different for these two domain. We will break down this integral into two parts. One is the x is negative, that is minus infinity to 0, another is x positive, so plus infinity to 0. So, it will be 1 over root over 2 pi minus infinity to 0, we will be putting e to the power minus plus a x e to the power I alpha x dx plus 0 to infinity e to the power minus a x e to the power I alpha x dx. So, if you carry out these integrals, I am not going to these integrals have to be carried out, then it will be e to the power a plus I alpha x dx. So, if you and then put the limits, final results you will be getting as 2 divided by root over 2 by pi a plus a square plus alpha square. So, that is the Fourier transform of the function f x is equal to e to the power minus mod x. Then we will take up one more example, that is Fourier sine transformation. Let us find Fourier sine transform on f x, and the definition of f x is equal to 0 for x lying in between the range 0 and a, this is equal to x for x lying in between the range a to b, and this is equal to 0 for x greater than b. So, we find out the Fourier sine transformation on this. So, f s alpha is root over 2 pi, that is root over 2 by pi 0 to infinity f of x sine alpha x dx. So, this is a definition of Fourier sine transformation. So, again we break down this problem into 3 sub problems, break down this integral into 3 sub integrals. One is from 0 to a f x sine alpha x dx, another is from a to b sine f alpha x f x dx, and then another is from b to infinity f of x sine alpha x dx. Now, if you look into the definition of f x is equal to 0 for 0 to a. So, this term will be 0 because f x is 0. So, anything multiplied by 0 will be 0. F x is 0 for x greater than b, b to infinity. So, this term will be also gone, and only one term will survive, that is a to b, where f x becomes x. So, this becomes root over 2 by pi integral a to b x sine alpha x dx, and this we can do integration by parts. So, this will be root over 2 by pi a cos alpha a minus b cos alpha b divided by alpha plus sin alpha b minus sin alpha a divided by alpha square. So, that is the Fourier transform, sine transform on f x. So, likewise, if f x any function is given, we can carry out the Fourier sine transformation, we can carry out the Fourier cosine transformation, we can find out the Fourier transformation as well on the function f x. So, this way by the definition of Fourier transformation, one can find out the transform in the alpha domain from the x domain. Okay. Next, we look into some of the properties of Fourier transform. First property is the linearity property. Fourier transform of two functions which are linearly additive, C1 f1 x plus C2 f2 x. This should be is equal to C1 f of f1 of alpha plus C2 f2 of alpha. F1 alpha is Fourier transform of f1 x, and f2 alpha is Fourier transform of f2 x. Now, the inverse is also true, inverse of this relation is also true. That means, f inverse C1 f1 alpha plus C2 f2 alpha is equal to nothing but C1 f1 x plus C2 f2 x. So, the linear relationship, if two functions are additive linearly, then Fourier transforms are also additive linearly with the same coefficient C1 and C2, and the inverse of this also you will get back the original functions with a linear form. Okay. So, that is the first property. The second property is that if f of alpha is Fourier transform of f of x, then Fourier transform of f of a x is 1 over a f of alpha by a. Okay. We look into the third property. If f alpha is Fourier transform of f of x, then Fourier transform of f of x minus a is given as e to the power I alpha a times f of alpha. So, these are the various properties of the Fourier transform. So, this is if f alpha is given by f x, if Fourier transform of f x, then Fourier transform of f x minus a will be nothing but e to the power this will be same as f alpha, but multiplied by e to the power a alpha. Okay. So, next we will look into the some of the properties of the derivatives, and these are very important, that we have looked into the Laplacian of Laplace transform of different derivatives in the earlier class. We will look into the Fourier transforms of various derivatives. The first one is, let us look into the Fourier transform of del u del t for x lying between minus infinity to plus infinity. Then we evaluate the Fourier transform of del u del t is, we put the definition of Fourier transform. This will be 1 over root over 2 pi minus infinity to plus infinity e to the power I alpha x del u del t dx. So, we take del, because this integration is over x. So, this derivative does not matter. So, we take this derivative out of this integral, but in that case, since we will be once we will be carrying out the integration over x, we are averaging out the x. So, therefore, this partial derivative becomes total derivative if we take this derivative out. So, this will be d dt of 1 over root over 2 pi minus infinity to plus infinity e to the power I alpha x u dx. So, this becomes d u dt, where u alpha t is Fourier transform of u as a function of x and t. So, that is the Fourier transform of the derivative del u del t. Now, let us look into the Fourier transform of del u del x and del square u del x square. They are very important. So, second property is Fourier transform of del u del x and del square u del x square for the domain x lying between minus infinity to plus infinity. So, let us find it out. Fourier transform of del u del x will be 1 over root over 2 pi minus infinity to plus infinity e to the power I alpha x del u del x dx. Then what we can do? We can carry out, we can evaluate this integral, we carry out this integral by parts. So, 1 over root over 2 pi. So, this will be e to the power I alpha x u minus infinity to plus infinity minus infinity to plus infinity, the first function, integral of the second function minus derivative of first function. So, e to the I alpha multiplied by e to the power I alpha x, integral of the second function u dx. Okay. So, now if we assume that limit x tends to plus minus infinity u of x t is equal to 0. This indication, this assumption simply indicates that u is a bounded function at infinity. So, it means that we are going to get a really a feasible solution. We are not going to get an infeasible solution where the solution blows out at x is equal to plus minus infinity. So, in order to have a physical solution, we have to utilize these two physical boundary conditions. Again, these are the examples of physical boundary condition. This simply indicates this boundary condition simply indicates that whatever we are going to do, the solution that we are going to have is a bounded solution, and it is a finite solution. Under any circumstances, it cannot go infinite in the domain of x. So, therefore, this is very important and we have to take care of this. So, we impose this boundary condition that at limit x tends to plus minus infinity, u at x, u as a function of x and t, it becomes 0. If that is the case, then we solve lots of this problem. So, f of del u del x is now becomes 1 over root over 2 pi minus I alpha. So, this term will be 0 because u at infinity it is 0, u at minus infinity it is 0. So, the rest term is 1 over root over 2 pi minus I alpha e to the power I alpha x u dx, e to the power I alpha x u dx minus infinity to plus infinity. If you remember what is this? This is nothing but the transformed Fourier capital U x alpha and t. So, this is a Fourier transform of u. This expression is nothing but the Fourier transform of u. So, we write it down as f del u del x should be is equal to minus I alpha 1 over root over 2 pi minus infinity to plus infinity e to the power I alpha x u dx, and this is nothing but capital U alpha t. So, this is a Fourier transform of u. So, it is minus I alpha u alpha t. Okay. Next property we see is the Fourier transform of del square u del x square. Del square u del x square, where x lying in between minus infinity to plus infinity. So, let us take the Fourier transform of del square u del x square, that is 1 over root over 2 pi minus infinity to plus infinity e to the power I alpha x del square u del x square dx. Now, again we do integration by parts. If we do integration by parts, let us see what we get. We will be getting 1 over root over 2 pi e to the power I alpha x del u del x. So, first function integration of the second function minus infinity to plus infinity minus I alpha integration e to the power I alpha x minus infinity to plus infinity del u del x dx. We assume, in order to have a bounded solution, we assume del u del x is equal to 0 at x is equal to plus minus infinity. So, if we put this boundary condition that slope of u is also equal to 0 at x is equal to plus minus infinity, then this term will be vanishing and you will be living with this 1. So, it will be minus I alpha 1 over root over 2 pi e to the power minus infinity to plus infinity e to the power I alpha x del u del x dx, and again we do integration by parts. So, minus I alpha 1 over root over 2 pi. So, this becomes e to the power I alpha x u minus infinity to plus infinity minus I alpha minus infinity to plus infinity e to the power I alpha x u dx, and u is equal to 0 at x equal to plus minus infinity. If that is the that we have already assumed in the earlier problem as well. So, under this assumption this term will vanish. So, we will be having I alpha square minus minus plus I alpha square. So, this becomes minus alpha square 1 over root over 2 pi minus infinity to plus infinity e to the power I alpha x u dx, and this becomes minus alpha square. This whole term becomes a Fourier transform of u. So, this becomes u capital U in alpha and t domain. So, that gives the Fourier transform of del square u del x square. Similarly, we can carry out the sine and Fourier sine and cosine transformation. So, we can carry out Fourier sine and cosine transform, and it can be found out that for evaluation of sine transformation of and cosine transformation of del square u del x square, we can find out the Fourier sine transformation of del u del x. We can find out the Fourier sine transformation of del square u del x square. We can carry out the Fourier cosine transformation of del u del x, Fourier cosine transformation of del square u del x square. Okay. So, it can be shown exactly the same way we have done earlier. That at x is equal to 0, u must be equal to 0 in order to have a bounded solution should be specified in case of sine transform and at x is equal to 0, del u del x must be is equal to 0 for cosine transform. That means, if we have a problem where this boundary condition appears u x at x equal to 0, u is equal to 0, we will be able to do a sine transformation. We can have a Fourier sine transform on both the sides. For a problem where it is specified that at x is equal to 0, del u del x is equal to 0, then we can have a Fourier cosine transform. So, these are very important. Now, based on these conditions, if these boundary conditions are specified, one can come to know that which transform one can apply, whether it is a sine transform or whether it is a cosine transform. Okay. Next, we do a problem of chemical engineering application. We look into the solution of diffusion equation. This problem says that del u del t is equal to k del square u del x square, but the domain of x is minus infinity to plus infinity. So, we have a transient one dimensional heat conduction problem. Now, if you remember, we have solved this type of equation using the separation of variable in the earlier classes. You must identify what is the difference between this problem and the separation of variable type of problem. The basic difference is, in this problem this represents transient one dimensional heat conduction, but the x dimension is pretty long. So, you have a very long plate across which the heat conduction is taking place. On the other hand, if you remember the problem definition of the whatever we have done earlier, one dimensional transient heat conduction problem, the definition remains the same, del u del t is equal to alpha del square u del x square, where here alpha is equal to k, alpha is nothing but the the thermal diffusivity. But if you remember the boundary conditions were at x is equal to 0, T u is equal to 0, and at x is equal to L or A, u is equal to. So, it is a finite domain in the case where we have solved the separation of variables. Here we are talking about an infinite domain. So, that is the difference between the two. So, the difference, let me write it down, then things becomes clearer. In one case, why we are taking Fourier transform, in another case why we are not taking Fourier transform, we are using the separation of variable. In this case, we are talking about heat conduction across a very long plate, infinitely long plate. On the other hand, the separation of variable type of solution, we had heat conduction occurring across a finite length plate. So, this is the difference between the two problems. Let me write down the boundary condition for this problem and initial condition. The initial condition is at t is equal to 0, u is equal to f of x. So, f is a prescribed function, it is a known function. Or it may be a constant as well. The boundary conditions are at x is equal to infinity, u is equal to 0 and del u del x is equal to 0, at x is equal to minus infinity, u is equal to 0 and del u del x is equal to 0. So, therefore, at x is equal to plus minus infinity, both u and del u del x will be equal to 0. So, this means the function temperature profile is a well behaved profile. It does not go to infinity at any place in the domain, even at infinite distance. So, it will basically die down there. So, it is a well behaved problem. So, we take the Fourier transform of partial differential equation del u del t is equal to k del square u del x square. So, we take Fourier transform on both sides. So, 1 over root over 2 pi minus infinity to plus infinity del u del t e to the power I alpha x is equal to dx is equal to k 1 over root over 2 pi minus infinity to plus infinity del square u del x square e to the power I alpha x dx. So, we have already looked into the Fourier transform of this derivative del square u del x square. We have already looked into the Fourier transform of this derivative del del t, and let us see what we get. So, this becomes du alpha t dt is equal to minus k alpha square u as a function of alpha and t. So, ultimately you will be getting du dt is equal to minus k alpha square u. We separate the variables, this becomes du by u is equal to minus k alpha square dt. Now, one can carry out this integration will be ln u minus k alpha square t plus ln some constant, integration constant a. So, ln u over a is nothing but minus k alpha square t. So, you will be getting u as a function is equal to a exponential minus k alpha square t. So, this becomes the solution of the transformed function. So, we write down the initial condition to solve this equation, because there is only one unknown here. So, at t is equal to 0, we had u is equal to f of x. Now, we have, since capital U is a Fourier transform variable, we have to take the Fourier transform of this initial condition as well. So, we take Fourier transform of this boundary condition. So, this becomes capital U is equal to 1 over root over 2 pi minus infinity to plus infinity e to the power I alpha x f of x dx. So, this is the Fourier transform of f x. We call this as f of alpha. If f x is specified, then we can take the Fourier transform of that. Suppose f x is x, then we can carry out the Fourier transform of that. If f x is different, let us say e to the power minus x square, then it will be different. So, let us define, depending on the expression of f x, we can have the Fourier transform of this equation. So, let us call this in general that Fourier transform of this initial condition initial condition becomes f of alpha. So, we put it here. So, at the solution is equal to a exponential minus k alpha square t. So, f of alpha is nothing but a. We put t is equal to 0 there. So, the complete solution in the transform domain becomes f of alpha e to the power minus k alpha square t is the solution in the transform domain, then what we can do? We can take the inverse transform and convert into x and t. So, this is in the alpha and t domain. We can take the inverse transform and convert into the x and t domain. So, we take the inverse transform. So, you will be getting u as a function of x and t is equal to 1 over root over 2 pi minus infinity to plus infinity f of alpha exponential minus k alpha square t e to the power minus I alpha x dx. So, when you take Fourier transform, we multiply it by integral I alpha x dx, and in this case when you take the inverse Fourier transform, we multiply it minus I alpha x d alpha. Okay. So, this will be 1 over root over 2 pi minus infinity to plus infinity f of alpha exponential minus k alpha square t e to the power minus I alpha x d alpha. In this integration, both x and t need to be treated to be constant. X and t are treated to be constant. So, we will be getting the Fourier transform of the inverse transform in x and t, and in fact, this turns out to be, after doing some mathematical manipulation, this becomes 1 over root over pi minus infinity to plus infinity f of x plus root over 4 k t z e to the power minus z square dz. So, it will be in that particular form, and one can get the inverse transform and can obtain the function, the solution u as a function of x and t. Okay. Next, we move over to the another example. So, let us look into example 2. So, this is again a flow in a semi infinite medium. So, if del u del t is equal to k del square u del x square, where the domain x lying between 0 to infinity and t greater than 0. Okay. So, this is the problem. Now, let us set up the initial and boundary condition. The initial condition is at t is equal to 0, u is equal to 0. At boundary conditions are at x is equal to 0, u is equal to u naught, at x is equal to infinity, u is equal to 0, and del u del x must be equal to 0. Now, if you remember that if we have, since we have at x is equal to 0, we have the Dirichlet boundary condition, that is u is equal to u naught, we should use you should take a Fourier sine transformation of this equation. Now, this boundary condition that x equal to infinity, u is equal to 0 and del u del x is equal to 0, it indicates that we have a finite solution even at infinite domain, and at x is equal to 0, u is equal to u naught. So, basically the variation of the dependent variable u is from u naught to 0. So, from infinite to 0. So, if you look into the profile of u as a function of x, this looks something like this. So, it is always a finite one. Finite profile. So, now we take the Fourier, since we have the so the finiteness of the profile is ensured by these two conditions located at x is equal to infinity, both u is equal to 0 and del u del x will be equal to, that means at infinity it will be asymptotically equal to 0. Okay. Let us look into this, come back to this problem. Since we have the boundary condition at x is equal to 0, we have a Dirichlet boundary condition. Dirichlet boundary condition is used. We must take Fourier sine transform. Okay. Now, you just take the Fourier sine transform of the governing equation, both sides of the governing equation. If you take that, then let us write down the equation under root 2 by pi 0 to infinity del u del t sine alpha x dx is equal to k root over 2 by pi 0 to infinity del square u del x square sin alpha x dx. So, we take the Fourier sine transform. So, we evaluate both these both sides, both the integrals by parts and see what we get. Integration by parts, this will be root over 2 over pi. Okay. Del t can be taken out. So, it will be d dt. Okay. So, 0 to infinity u sin alpha x dx. Okay. So, that will be the Fourier sine transform equal to k root over 2 by pi. So, sin alpha x first function, integration of second function will be del u del x evaluated from 0 to infinity minus differential of the integration of differential of first function, that means alpha cosine alpha x, and integration of the second function, that is del u del x dx. Okay. So, let us see what we get on the left hand side. In the left hand side, we get the Fourier transform of Fourier sine transform of u. So, it will be d u s dt, where u s is nothing but function of alpha and t, and this will be k root over 2 by pi sin alpha x del u del x. So, when you put the infinity, then we had the condition del u del x at infinity equal to 0. When you put x is equal to 0, then sin 0 is equal to 0. So, this term will not be contributing anything. So, let us put these boundary conditions one again and explain. Let us put at infinity. At infinity, this will be sin alpha infinity del u del x evaluated at infinity. If you remember, we had the boundary condition, bounded boundary condition, finite boundary condition, that at x equal to infinity, u is equal to 0 and del u del x is equal to 0. So, at x is equal to infinity, we have del u del x is equal to 0. So, that term will be off. When you put the lower limit, that at x is equal to 0, sine alpha x is equal to 0, sine 0 is 0. So, both these terms at these two limits will vanish. So, these will be contributing nothing. So, we will be having minus alpha integral 0 to infinity cosine alpha x del u del x dx. Again we do integration by parts. This is the first function, this is the second function, k root over 2 over pi minus alpha second bracket, first function integral of the second function cosine alpha x u. So, this is from 0 to infinity minus integral derivative of first function. So, this will be minus alpha sine alpha x minus minus plus alpha sine alpha x and integration of the second function, that is u dx from 0 to infinity. So, k root over 2 by pi, this will be minus alpha. When you put x is equal to infinity, then cosine alpha infinity and u at infinity, but u at infinity, if you remember the boundary condition that x at infinity it will be equal to 0, and if you put the other boundary condition that so if you put the first boundary condition, this becomes 0. If you put the second boundary condition, this become cosine 0 is 1 and u at x is equal to 0. If you remember the boundary condition, u at x is equal to 0 is u naught. So, we have this okay. So, there is a second bracket ends here plus alpha integration 0 to infinity sine alpha x u dx, second bracket ends here, then third bracket. So, let us see what we get. We are getting as k alpha k root over 2 by pi okay, minus minus plus alpha u naught minus alpha square and this will be nothing but sine 0 to infinity sine alpha x u dx. This is nothing but the sine transform of u. So, this becomes u s alpha t. Okay. So, okay, still now it is not u s, when it will be multiplied by root over 2 by pi. So, I write this integral here 0 to infinity sine alpha x u dx. Okay. So, let us write it neatly. So, d u s dt is nothing but k alpha u naught root over 2 by pi minus alpha k alpha square root over 2 by pi 0 to infinity sine alpha x u dx, and this whole term is nothing but the Fourier sine transform of u. So, d u s dt is equal to k alpha root over 2 by pi u naught minus k alpha square u s. So, we take it to the other side, this becomes d u s dt plus alpha square k u s is equal to k alpha square k alpha u naught root over 2 by pi. Okay. Now, if you look into the solution to this problem, we know this solution can be obtained by breaking down the problem into the homogeneous part and non-homogeneous part. So, you can obtain this thing by you can take it to the other side and can get it done. So, d u s dt is equal to minus k alpha square u s plus k alpha u naught root over 2 by p, bring it to the in the denominator and just integrate it out. So, you will be having u s as a function of alpha and t. So, it will be root over 2 by pi u naught by alpha 1 minus e to the power minus k alpha square t. So, that is the solution of u s as a the sine transform of in the as a function of alpha and t. So, you will be getting u as a function of x and t once you take the Fourier sine inverse of u s alpha t. So, inverse Fourier sine transform. Now, let us do a little bit of inversion of Fourier sine transform. You will be getting u as a function of x and t is root over 2 by pi 0 to infinity u s alpha t sin alpha x d alpha. So, this will be root over this will be 2 by pi u naught by alpha 0 to infinity sin alpha x divided by alpha u s. We just put the solution 1 minus e to the power minus k alpha square t d alpha. Again we do an integration by parts. So, this will be 2 u naught by pi alpha and this will be 0 to infinity sin alpha x by alpha d alpha minus sin there will be no alpha here. So, there is no alpha there sin alpha x by alpha e to the power minus k alpha square t d alpha from 0 to infinity. So, we will be having 2 u 0 pi divided by pi. This integral is nothing but pi by 2 minus this integral is nothing but pi by 2 error function of x divided by root over 2 k t. So, you can look into the table of Fourier sine transform. You will be seeing that this integral is nothing but the error function of x by root over 2 k t. So, that gives the complete solution of u as a function of x and t using the Fourier transform. So, let me conclude whatever we have done. We have come to the end of our course. We have looked into the mainly we have looked into the two domains. One is the discrete domain, another is the continuous domain. In discrete domain, we represented all the equations in the form of matrix. We looked into several solutions of non-homogeneous partial non-homogeneous algebraic equations, homogeneous ordinary differential equations, non-homogeneous ordinary differential equations. We looked into several tools, eigenvalues and eigenvector methods to evaluate them. We looked into the stability analysis of a chemical engineering process. Then again we came down to the continuous domain. In the continuous domain, we classified the partial differential equations and looked into the various methods for the solution of partial differential equations. It will be first we studied in detail the separation of variable type of solution method, and we developed the theory for that and used them for solution of problems for both homogeneous, non-homogeneous, all kinds of boundary conditions. And then we looked into the non-homogeneous partial differential equations, but linear using Green's function method. Again we developed the theory of the Green's function and applied them for the solution of parabolic partial differential equations and elliptical partial differential equations. Then we looked into the similarity transformation method, looked into the integral methods, Then we looked into the integral transforms like Laplace transform and Fourier transforms, and how they will be utilized for solution of chemical engineering problem, a realistic problem in multidimensional system. So that gives a complete coverage of the syllabus, whatever we have done, we are supposed to cover in this course. And I hope that this course will be of use to you whenever you will be dealing with actual chemical engineering problems in future. And with that, I just finish this course, and I wish best of luck to all of you. Thank you very much.